Welcome back. Good news and bad news. This is the last session of the day at the conference. And we start now with Uzi Pereg, who will talk about MAC, right? Multi-access channel, MAC.
Exactly, yes. So this is a network setting where two transmitters send to one receiver. And we'll look at the case where there is entanglement resources between them. This is a joint work with Christian Deppe and Holger Boche. So I'll give some background. Recently, there is significant interest in how quantum entanglement can be used in classical networks. This could be very useful because then we can keep the infrastructure classical and only have some components that are quantum. Now, if we look at the performance, if we look at the case of a single user channel, as Paula discussed in the previous session, then entanglement resources do not increase the capacity if we look at the classical channel. And entanglement between the transmitter and the receiver. Although it can increase the zero error capacity, which means that it affects the error probability in general. Now, when we move to the multi-user case, two users, we look at the MAC, at the multi-access channel. And then in this case, entanglement resources between transmitters can increase the achievable rates even for a classical channel. This was demonstrated by Felix and others using pseudo-telepathy examples and also adversarial examples by we can also look at a more general framework where there are non-signaling correlations between the transmitters. And then there's this very recent result about Fauzi and Ferment showing that for this very fundamental channel, the binary adder channel that just adds the input, non-signaling correlation can increase the achievable rate, but whether entanglement can also do that, that's an open problem. In previous work, we also looked at the broadcast setting and showed that when we have entanglement between receivers, it doesn't increase the achievable rates. Although in sensing, we do know that it can improve the sensitivity, so maybe here it might also affect the error probabilities, but we currently don't know. Now, in the classical literature, there are also a lot of different forms of cooperation between the transmitters. One of the models is called conferencing transmitters, but in this case, the transmitters can communicate with each other. They can send messages to one another over rate-limited links, and there are many classical works on those on models of conferencing transmitters. And the case of classical quantum channel was considered by Boche and Entangled. Okay, so what do we do in this work? Our main contributions are the following. We consider communication over a map with entanglement between the transmitters, and we try to characterize, although it's a partial characterization of the capacity region for a general multiple access channel. And we show that the previous results of Felix in particular can be obtained as a special case. And we observe that as opposed to the classical setting, the capacity region is the same whether we consider a maximal error criterion or average over the messages. In the classical setting, a while ago, Duke has shown that the regions are not necessarily the same, but with entanglement, they are the same. I'll also, if time permits, I'll also give a few comments about the case when there are also conference transmitters. Okay, so now I will present the channel model. So we have a classical channel, which is specified by this probability function, P of y given x1 and x2. Okay, so we have two transmitters, two senders, Alice1 and Alice2. Their inputs are x1 and x2 to the channel, and one receiver, Bob, that observes the output y. Now, in the classical model, without entanglement, Alice1 maps her message N1 to a code block X1 of length N, and similarly for Alice too. She has a different message, M2, and therefore she will also have a different coding rate. Then the code words are sent through the channel, and the decoder maps the observation YN to the estimation of both messages. So it looks like this. Okay, here the transmitters are F1 and F2. Then we see the messages M1 and M2 mapped to the transmissions, and the decoder receives YN and estimates the two messages. Here, however, we add entanglement resources. We assume that there is a pre-shared entangled state, meaning before communication begins, before the senders even have the information that they would like to send, they share this entangled state psi, and the entanglement resources are E1 and E2. So in this case, the encoding operation is really a measurement. Each transmitter measures her entanglement resource depending on the classical message that she would like to send. Skip a little bit. So we have two measurements, one for each transmitter. Formally, it's specified by a POV, one for each transmitter. The decoding function is the same as in the classical case. If for given measurement, this induces some joint probability distribution of the inputs, and then we can compute the error probability, additional error probability. And now I'd like to remind you, we have two messages, M1 and M2, that are independent, one for each user. Therefore, we have two coding rates, R1 and R2. So we say that the pair R1, R2 is achievable if we can communicate that those rates reliably, that is, with an error probability that tends to 0. And now, this is really the standard definition. The capacity region is really the collection of all rate pairs that we can achieve. So I'll begin with very basic remarks. In communication, sometimes we think of entanglement as a quantum version or something that generalizes common randomness, or in this case, sharing a random key between the transmitters. And indeed, the most basic use of entanglement is in order to generate a random key. However, in our setting, if we don't have entanglement, if we only have a random key, classical correlation between the transmitters, the capacity region remains the same. On the other hand, based on the previous result, we know that entanglement can improve the achievable rates, and I will also show this example very soon. But before that, I would like to give the general results. So I will start with what we call inner and outer bounds, although we can also call them lower and upper bounds. So this is the inner bound. We denote this region by R. We see here that the rates are bounded by those three mutual informations. And this really resembles what we have, the capacity region that we have without entanglement. But here, the difference is that here V1 and V2 are not the inputs of the channel, they are not X1 and X2. Instead, they are auxiliary variables. Now, I'll also define another region, O, this will be the outer bound. You can see that the rates, the bounds are, the constraints are the same. So what is the difference between those two regions? The difference is in the joint distribution of the auxiliary variables, V0, V1, and V2. In the outer bound, we look at any joint distribution. In the inner bound, this is really the limit of a limitation of a Markov relation. Even V0, V1, and V2 are independent. Now, this is not the whole story. We have here a union over an entangled state and a pair of measurements. So the union is over the entangled states phi of two auxiliary quantum systems as well, A1 and A2, or ancillary. And as I said, use classical auxiliary variables and a pair of POVMs, L1 and L2, that produce the inputs X1 and X2 as measurement results, conditioned on V0, V1, and V0, V2, respectively, for transmitter 1 and transmitter 2. And then, given those three objects, we can compute the joint distribution of these two. Okay. Now, in general, when we have a union over auxiliary variables, if there's any hope to compute this region, we need a bound on the alphabet size of those auxiliary variables, because they are not part of the problem, they are not part of the model, they are only inside the formula. They're also called external variables. So we show that the union can be exhausted, it can be restricted to variables with those bounded alphabets, and we can also restrict ourselves to pure states. The second part is based on purification, as expected. And the first part, the alphabet bound, cardinality bound, is based on the support lemma, also called the Kara-Theodori. This is what the support lemma says, or one version of the support lemma. Any point in the convex closure of a connected compact set within RD belongs to the convex hull of D points in that set. This is, for example, why we have three, because we have three constraints and we can reduce the output to that. Now, this is not all that we have. We also have quantum auxiliary systems, A1 and A2. We would like to have a bound on the dimension of those auxiliary quantum systems. We observed that it is impossible. Why is that impossible? This is closely related to the Searleson problem, or the Searleson conjecture, that states that the set of correlation families, the set of distributions P, conditional distributions, that are obtained from local measurements on an entangled state, where we look at the set for all possible entangled states, and we take the dimension of the entanglement to be larger and larger. The conjecture says that this is a closed set. So we can get close to, if we take the dimension to be large enough, we can get close to the limit. This theorem says that the Searleson conjecture is actually false. It's not a closed set, and there are different proofs for different versions of this conjecture. There's a weak version, a strong version. Basically, the proof shows that there exists a family of refereed games such that it is undecidable to determine if there exists a perfect strategy for the game in the family. So if you look at this, we think of V1, V2 as the questions that the referee sends to players, and the players in turn respond with X1 and X2 as answers. Okay, so this is our main result. We showed that the capacity region is bounded between the region R and the region O. And then we also give regularized characterization using the region R. So the achievability proof is fairly simple. We prepare a product state, use random code books, and measure it using product measurements. But as I said, we cannot actually compute the region R. One may ask, is it even useful? Well, it is useful in the sense that if we limit ourselves to an entanglement rate, theta E, so a given dimensional entanglement, then we can compute achievable rates. If we just choose, for example, if we just choose an entangled state and compute and distribution and measurement, then we can compute this and we have achievable rates. So by simply choosing. We cannot compute the best achievable rate in this case. Okay, now I will give two examples, but they are actually not my examples. They are the examples from the previous work. So the examples are given in terms of a referee game. There's a referee that selects questions V1 and V2, let's say uniformly, and he gives V1 to the first player, Alice, and she responds with a W1, and he gives V2 to Bob, the player 2, and he responds with W2. The rule of the game is that they win if this 4 tuple belongs to a set that we call the winning set of the game. One simple example is the game that was presented by Peres and Merlin, the Magic Square game, where we have a square that consists of 9 cells. The referee chooses one cell. So he has a row I and column J, uniformly at random. Then he asks Alice to fill the ith row. So I is the question of Alice. And she needs to fill the ith row with 3 bits that have even parity. Similarly, Bob receives J and he needs to choose 3 bits with odd parity. Let's look at an example. If the referee has chosen 2 and 1, then Alice can choose those 3 bits. They have even parity. And those 3 bits of Bob have odd parity. But now we say that they win the game if they agree on the overlapping cell. So the strategies that are gave as an example lose the game because Alice has chosen 0 and Bob has chosen 1 for the overlapping cell. In order to guarantee winning, they need to meet before the game starts and fill the table. Now you can check that you cannot fill 9 bits in this table and satisfy the constraint. You can fill 8 bits, but then you will be stuck in the 9th cell. So you cannot guarantee winning. But what if we look at, instead of looking at deterministic strategies, let's suppose that they randomize and then we look at the probability of winning. This is bounded by 8/9, and I think it makes sense, right? It's not that surprising. And now let's add correlation. Okay, first we look at classical correlation. We give them a key with 1,000,000 bits. Doesn't matter how many bits. Still, it turns out that the probability of winning is bounded by 8/9. Okay, but now quantum correlation, entanglement. Given entanglement, they can win the game with probability 1. This is why it's called pseudo-telepathy game. Now, in order to show this, you can use this product of EPR states. So they are using 2 cubic pairs, 2 entanglement bits, if you wish. And then they measure in those bases. And all we need to do is convert plus and minus to 0 and 1. And we can win the game with probability 1. Okay, so now in the previous work of Leditsky et al., they defined a magic square game. So in this game, the input alphabet x1 is the question, the row, and the response of Alice and of the first player. And the input alphabet of the x2 is really the question and the response, the column and the column index and the column itself that Bob gives. And now we define the channel relation as follows. If this tuple of questions and answers wins the magic square game, then Bob receives the questions, the row and the column, perfectly. But otherwise, if they lose the game, then Bob gets pure norms, a uniform distribution over the magic square. So without entanglement resources, the classical case, the bound on the sum rate was recently improved by Sashadri et al. They showed that the sum rate is bounded by 3.02. And since we can win the magic square game with probability 1, then we can achieve, given entanglement, we can achieve this sum rate of 2 times log 3, which is about 3.17, about 5% increase in the sum rate. And we can also get it from, if you plug in our result, our region, uniform distribution, and EPR pairs, then you also get this region. Sorry. And we see that it requires an entanglement rate of 2. Okay. Now, another interesting example from the previous work is a game that is based on a system of linear equations. This is a game that was introduced by Slofstra and Vitti. And in this game, it turns out that in order to win with probability 1 minus E minus T, you need an entanglement dimension that is bounded as we have here, that is larger than this, which implies that in order to win the game with certainty, with probability 1, you need an infinite amount of entanglement. You need an infinite entanglement dimension, and therefore this also coincides with the case that I mentioned earlier, where the auxiliary systems also have infinite dimension. We also use this entropy continuity bands to get an achievable region for a finite entanglement rate. And okay, and now I would like to give this observation about average versus maximal error criteria. So in network information theory, in general, we need to distinguish between the capacity when we look at the maximal error, when we maximize overall messages, or an average, a message average error, where basically we assume that the messages are uniformly distributed. So we will denote the capacity regions by C and C bar. So in general, the capacity region for a maximal error is a subset of the message average capacity region. Now, in the single user case, we know this since Shannon that the capacities are the same for both criteria, error criteria, but Duke has shown that there exist multiple access channels where the regions are not the same. Or in other words, the maximal error region is a strict subset of C bar, of the message average error. This is the example that Duke has used. It kind of resembles an erasure channel. It's called contraction channel. And here we show that given entanglement persistence, the regions are the same. The proof follows Chai's and resembles the robustification technique, where we use the entanglement to generate a very small key, and then the average over the key, a shared key between the transmitters, kind of replaces the averaging over the key. Now, we also considered another model where, in addition to entanglement, there is also conferencing between the encoders. This means that there are bit pipes, noiseless links that have limited capacities, C12 and C from 2 to 1. And now we can look at the capacity region for this model. I'd like to point out that both entanglement and common randomness are non-signaling resources. We cannot use them to communicate by themselves. Whilst conferencing is stronger in this sense. The transmitters communicate with each other. So one can ask, although it's kind of a heuristic question, whether conferencing at a low rate is necessarily better than entanglement at a high rate, and then based on the previous result, based on the magic square result, we see that the answer is no. Another setting that we consider is cubic pipes. Okay, quantum conferencing between the transmitters. They can send qubits to each other, while the channel itself is still classical. And then we observe that if we have this plus entanglement, then each transmitter can use superdense coding to double the conferencing rate. So I'll conclude here so that there will be time for questions. We consider communication over two-user multiple access channel with the entanglement sources between the transmitters. We partially calculate the bounded capacity region for a general multiple access channel. We show the bound of the auxiliary variable, but observe that it is impossible to bound in general the dimension of the auxiliary quantum systems. And this is closely related to the zero-sum problem and also this complexity result of MIP star equals RE. We showed that the previous results are special case. The magic square result of Leditsky et al. Showed that we can get strictly higher rates than the capacity. And the second example that they gave shows that the achievability may require infinite amount of entanglement. And we observed that in the that with entanglement, the capacity regions are the same, whether we consider whether we consider a maximal error or an average error. At last, we've seen that the entanglement can increase conferencing when we have qubit heights between the transmitters. Yes.
I want to point out that actually, even in the classical case, the average and maximal are the same for stochastic, of course.
When they share a key, yeah, that's good. Yeah, and the proof will basically use that shared key. That's correct. Yes, that's correct.
I'm just wondering if it would be possible to generalize the two-party multi-access channel for this magic square game when we expand the magic square to three tensor products or four tensor products of this.
I think that's an interesting question. I'm not aware currently of a generalization of it in the game. But then if you define a more general game with, I don't know, k players, maybe you can try to generalize it to generalize the multiple access channel as well. That's an interesting question.
Yeah, I mean, like, there's this result that generalizes this magic square game. Interesting.
Very well. I'd be happy to hear about it. Yes.
Question? Yep.
So at the very beginning, you mentioned something about broadcast channels as well. And what happens with the technologies there where it doesn't help. Could you repeat that?
Yeah, to be honest, it was an observation within a longer paper because if you think about it, it's actually very straightforward.
But what's the statement? Sorry.
Okay. The statement is that if each receiver, okay, in the broadcast we have one transmitter sending information to receiver. So if each receiver shares entanglement with the other receiver, then it will not increase the region.
Okay,
now
it's like byte or
without communication between us. It's the mirror image. So I think for some people it may be tempting to think that since it's a mirror image, it might increase in that case as well. And there are in the classical literature some mirror results where you get results on the broadcast channel from the multiple access and vice versa. But the reason that it doesn't help with it is that in the broadcast case, the entanglement resources have no correlation with the messages or the channel inputs, and therefore the channel outputs are not even correlated with the entanglement resources. So if you go by the usual converse proof, it just goes away in the mutual information that you have there.
Okay. Yep. Yeah.
Yes. I mean, even in the special case of the degraded broadcast channel, or if you look at the degraded message set in one common message and one private message, still it doesn't have none of the fifth. Thank you.
Let's thank him again.